Now I am going to start module 1 of chapter 3. Chapter 3 is devoted to the theory of second order partial differential equation. The discussion with second order partial differential equation is important because second order partial differential equation arise in many problems in mathematical physics. This type of equation arrives to describe wave motion, diffusion equation and electric flow, fluid flow, etc. The entire chapter is divided into 3 modules. In first module, I shall discuss about origin of second order differential equation, and we shall show that how a second order equation can arise from starting from a solution. In module 2, we shall discuss about the solution of a second order PDE with constant coefficients, and we shall also discuss in module 2 a special type of with variable coefficient which is known as Cauchy-Euler form, and we shall show that with some transformation in independent variables we can transform the equation to a second order equation with constant coefficients. And lastly, in third module we shall discuss about the canonical form of a second order differential equation, and we shall derive how to obtain the canonical form from a given equation, and in this way we shall finish chapter 3. So, let us go to the first slide of module 1 of chapter 3. Now, I am going to discuss origin of a second order equation, that means how a second order partial differential equation can be generated from a solution. So, first take one example, let z is a function of x, y such that z equals to fu plus gv plus w, where f and g are some functions of u and v, and u, v, w are functions of independent variables x and y. In the entire discussion, we are bounded to take the 2 independent variables. So, here in this discussion we have only 2 independent variables which are denoted by x and y. Let small p be del z del x and q is del z del y, small r is del 2 z del x square, s is del 2 z del x del y and t is del 2 z del y square. These are the standard notation which are used in the theory of PDE. So, let us first take derivative of equation 1 with respect to x. Here z is our dependent variable. So, if we take differentiate with respect to x, then del z del x equals to f dash u into del u del x plus g dash v into del v del x plus w x. Now, if we take derivative of equation 1 with respect to y, so del z del y which is q is equals to f dash u e y plus g dash v v y plus w y. Now, thus we obtain equations in 3 taking derivative of equation 1 once with respect to x and y. Now, we take derivative of equations which are written in 3 with respect to x and y again. So, we take the first equation r which is del 2 z del x square, which is obtained by differentiating p with respect to x, and the equation is written in equation number 4. So, if we take the derivative with respect to y of the equation p equals to f dash u u x plus g dash v v x plus w x, we obtain the equation s equals to f double dash u u x u y plus g double dash v v x v y plus f dash u u x y plus g dash v v x y plus w x y. Now, if you take derivative with respect to y, the equation which is written as q is equal to dot dot, we get the equation t equals to f double dash u u y square plus the terms which are shown in equation number 4. Thus, we obtain 5 equations taking derivative of equation 1. Now, in these 5 equations the unknowns are the function f and g. So, we eliminate the derivative f dash, g dash, f double dash and g double dash from these 5 equations, and we obtain the relation, the determinant, which is written in equation number 5. Now, if we expand this determinant with respect to the first column, then we obtain a relation in the form which is written in equation number 6, capital R smaller plus capital S small s plus capital T small t plus capital P small p plus capital Q small q equals to W. And these capital R, capital S, capital T, capital P, capital Q and capital W are functions of independent variables x and y. So, if we observe equation number 6, we can see that from equation number 1 we obtain equation number 6, which is a second order linear partial differential equation. So, we can say that if we observe equation 1, there are two unknown functions f and g. So, if there are two unknown functions, taking derivative of that equation, we obtain a PDE of second order, which is written in equation number 6. So, let me take one example. Let z is some function of f and g, where f and g are some unknown function and f and g are function of x plus ay and x minus ay respectively. Now, we want to form a partial differential equation from the equation 7. So, for that purpose we take derivative of equation 7 twice with respect to x. So, we obtain the relation r equals to f double dash plus g double dash, and if we take derivative with respect to y of equation 7, we obtain the relation t is equal to a square f double dash plus a square g double dash, and from these two equations if we eliminate f double dash and g double dash, we obtain a relation of the form small t equals to a square small r, which is a second order linear partial differential equation. So, using this example we also see that if the original equation which is written in equation number 7 contain, if z is written as sum of two unknown function, then from that function one can obtain a partial second order partial differential equation. Now, this concept can be generalized for n number of functions. Let z is sum of n number of functions fr, vr, where fr are some unknown functions and vr are some functions of x and y. So, from this equation, from this relation one can lead to an nth order linear partial differential equation. In the last section we have discussed the origin of a second order PDE, that means how a second order PDE can be generated starting from a solution and how they are linked with each other. Now, I am going to discuss the application of, not application, how a second order differential equation can come in some physical problem. I shall take two examples, one from electric flows and another from electronics, and how a second order equation can come to solve this type of problem, that I am going to discuss. So, go to the slide show. First, I shall take one example from electric flow. For that, we consider a one dimensional flow of electricity in a long insulated cable, and I is the current, E is the corresponding voltage. Since there is a one dimensional flow, so in spatial direction there is only one coordinate which is denoted by x, and we have another variable which is time t. Thus, for the fall of potential in a linear element of length delta x situated at the point x, can be written, the equation can be written in this form: minus delta E equals to I R delta x plus L del I del T delta x, where R is the series resistance per unit length and L is the inductance per unit length. Now, if C is the capacitance to earth per unit length and G is the conductance per unit length, then we have the another equation for the current minus delta I equals to G E delta x plus C del E del T del x. Now, from the above two equations, we can obtain these two partial differential equations, del E del x plus R I plus L del I del T equals to 0. So, this equation can be obtained from the first equation dividing it by delta x, and the second equation can be obtained from the equation which is written here, minus delta I equals to G E delta x plus C into del E del T del x, and dividing this equation by delta x. So, we obtained two equations with two unknowns E and I. Now, we want to obtain the equation with one unknown variables. So, for that we differentiate equation 9 with respect to x to obtain the equation which is written in equation number 11, and we obtain equation number 12 from equation 10, taking derivative with respect to t of the equation 10. Now, from the equation 11 and 12, if we eliminate del I, the variable I, that means from the equation 11 and 12, one can eliminate del 2I del x del t, and del I del x can be eliminated from the equation 10. So, from equation 10, 11, 12, eliminating the variable I, we can obtain a relation which is written in equation number 13, del 2E del x square equals to L C del 2E del t square plus R C plus L G into del E del t plus R G E, and this equation is known as telegraphy equation, and this is an equation with unknown function E. Similarly, from the equation, from the above equation 9 and 10, if we differentiate the first equation 9 with respect to t and equation 10 with respect to x, we obtain the equations which is written here: del 2E del t del x plus R del I del t plus L del 2I del t square equals to 0, and del 2I del x square plus G del E del x plus C del 2E del x del t equals to 0. And from these equations, if we eliminate the variable E, one can obtain an equation in variable I to the equation which is similar to the equation 13, only E is replaced by the variable I. That means one can say that the equation 13 is satisfied by the current I. Therefore, E and I both satisfies the equation 13, which is known as telegraphy equation. Now, I want to discuss some particular cases of the telegraphy equation. Suppose the leakage to the ground is very small, and then for that case we can assume that G and L both are equivalent to 0, and if we put G is equal to 0 and L equals to 0 in equation number 13, one can see that 13 reduces to the equation del E del t equals to k del 2 e del x square, where k equals to RC to the power minus 1. This equation is also called telegraphy equation, but it is mostly known as the heat conduction equation or division equation in one dimension. And there is another particular case. Suppose we are interested to high frequency phenomena. So, for that case time derivative is most important. So, one can assume r equals to 0 and g equals to 0 in equation number 9. So, if we assume r equals to 0 and g equals to 0 in equation 9 and 10, we can get equation which is written here, del 2 e del t square equals to c square del 2 e del x square, where c equals to LC to the power minus half, and this equation is known as wave equation. So, here we see that for electric flow we get two second order partial differential equation. Now, I am taking one example from electronics where one can get second order PDE. So, in electronics we are considering this example. So, according to Gauss law of flux of electric vector E out of a surface S which bounding an arbitrary volume V is 4 pi times the charge content in the volume V. So, that can be written in the integral form like integration of E ds over S equals to 4 pi integration of rho dV. In the left hand side the integration is the surface integration and in the right hand side it is volume integration, and rho is the density of electric charge. And all of we know that Gauss divergence theorem says that surface integration of E over the surface S is equals to divergence of the function E over the volume V, which is written here. So, if we use the Gauss theorem, then we obtain the surface integration of divergence E dV is equal to 4 pi times integration of rho dV over V. So, if we compare both sides, then we get divergence of E is equal to 4 pi rho. Now, if we assume that E is derivable from a potential phi such that E is equals to minus of grad phi, then substituting this expression in the above equation, we get an equation which is written in equation number 15, grad square phi equals to minus 4 pi rho, and this is a famous equation which is known as Poisson's equation, and this is again we are getting a second order partial differential equation, and this is a linear equation, and if there is no any charge, then rho can be assumed as 0, then 15 is reduces to an equation grad square phi equals to 0, and which is known as Laplace equation or the harmonic equation. So, taking two examples, we have shown that in both the cases we are getting a second order partial differential equation and which are also linear. Now, I am taking few examples to illustrate that how a second order differential equation can be obtained when the dependent variable is sum of two unknown function. So, let us take this example. Let Z is sum of two unknown function f and g, where f and g are function of x square minus y, x square plus y respectively, and we do not know the functional form of f and g. So, they are arbitrary function. So, from this relation we want to get a partial differential equation. So, for that we first take derivative of the functional relation with respect to x. So, we get del z del x as 2 equals to 2x f dash plus 2x g dash, and if we take derivative with respect to y, we get del z del y equals to minus f dash plus g dash, and taking derivative with respect to x once again the first equation, we get del 2z del x square equals to, the expression is written here. So, from this equation we want to obtain a functional relation between the derivatives. So, for that we need to eliminate the unknown functions, but in these equations the unknown functions are present in the form of derivatives. So, we need to eliminate f dash, g dash, f double dash and g double dash. So, the expression for del 2z del y square can be obtained in the similar way. So, if we eliminate these functions f and g and their first order derivative and second order derivative, and if we compute this del 2z del x square minus 1 by x del z del x is equals to 4x square del 2z del y square. So, this is again second order differential equation. So, we started with a functional form where z is sum of two unknown function. So, eliminating these two unknown function, we are getting a partial differential equation of second order. Now, we are taking another example where z is sum of a function phi and its derivative phi dash. So, from this equation we want to obtain a partial differential equation. So, for that, so take z equals to 1 by x phi plus phi dash. If you take first order derivative with respect to x of this equation, we obtain del z del x equals to minus 1 by x square phi minus 1 by x phi dash minus phi double dash, and we have to take the derivative with respect to y. So, del z del y is equal to 1 by x phi dash plus phi double dash, and we take the second order derivative of z with respect to x to obtain the expression which is written here, and we also need to take the second order derivative with respect to y. Del 2z del y square equals to 1 by x phi double dash plus phi double dash. So, from these four equations, del z del x, del z del y, del 2z del x square, del 2z del y square, if we eliminate phi, phi dash and phi double dash, we can easily get that del 2z del x square minus del 2z del y square equals to 2z by x square. So, taking this example, we also see that if z is sum of a function and its derivative, the partial differential equation corresponding this functional form is a second order partial differential equation. Thus, in this model, we have discussed the origin of a second order partial differential equation. We have seen that if a function or the dependent variable z can be written as sum of n unknown function, this corresponds to a nth order partial differential equation. And we shall also take two examples, one from electric flows and one from electronics, to derive a second order differential equation for a physical problem. There are many examples where this type of second order differential equation arise in practice. So, in this way we end module 1 of chapter 3.